All right, let's go ahead and look at this problem I wrote down. So find all equilibria of this differential equation, dn dt equal to n minus 3 times n minus 1 squared and n minus 5 cubed. I think they should be relatively obvious. We're going to find them by setting it equal to 0. So we just set dn dt equal to 0, which is going to lead us to setting n minus 3 times n minus 1 squared times n minus 5 cubed equal to 0, which is going to give us n equal to 3, n equal to 1, and n equal to 5. Plus, the reason I really asked this question is I want to talk about classifying these equilibria, specifically because one of them is kind of weird. So if we classify them, and we're going to draw the phase plane here. So let's draw the phase plane. So again, on our vertical axis, we have our dn dt. On our horizontal axis, we have our n. And really, we should just think of like these as our x-intercepts or horizontal axis intercepts. So 1, 3, and 5. So there's our intercepts, 1, 3, and 5. And then we're going to graph the curve here. And I'm just going to note that if you plug in 0, 0 minus 3 is negative, 0 minus 1 squared is positive, 0 minus 5 cubed is negative, negative, positive, negative. Overall, it's going to be positive. I don't actually care about the value. I just care about getting the sign right. So it's going to be positive up here. And then at 1, since the power of the factor that 1 came from is even, we're going to bounce off. And then at 3 and at 5, we're going to cross through the horizontal axis here. So it looks something like this. Bouncing off, crossing through, crossing through. As we've seen a few times now, if d and dt is positive, that means n is increasing or going to the right. If dn dt is negative or below the horizontal axis, that means n is going to the left. Positive right, positive right. What's that pen doing? So let's classify the easy ones first of all. And I guess I should have said these were n hats technically, right? That's the notation we use for equilibria for whatever reason. It's not super duper important, but it is typical. So for n hat equal to 5, well, are the arrows pointing towards 5 or away from 5? Away, so it's unstable. So that's unstable. For n hat equal to 3, the arrows are pointing towards it. Oh, this red pen is killing me. It's got like all the ink in the world, and I don't know why it's not writing. Anyway, n hat equal to 3 is certainly stable since all the arrows are pointing towards it. Now, what about 1? Well, some of the arrows point towards it, some of the arrows point away from it. But the problem is you can't, it's hard to kind of like get pushed towards 1 and then stop right at 1. Right? Like if you get pushed just slightly too far, you're going to keep going. So 1 is also unstable. Basically, the arrows from both sides have to point towards it to be a stable equilibrium. This is definitely an unstable equilibrium. It's also unstable. So just FYI. If you have one like that, where not all the arrows are pointing towards it, it is still unstable. No, that's next quarter. Next quarter, we'll talk more about kind of what that's representative of, but that is not this quarter. So there were some questions about the homework, section 7.1 and 7.2. We'll take a look at those before we move on to talking more about solving differential equations, which we talked a little bit about last time, but we'll get more into today. So the plan for today is to do that, talk about solving differential equations. The plan for Tuesday is to review for your exam that is on Wednesday. That could entail going over the practice exam that I wrote, but I do plan on recording a video of solutions and also posting solutions. So we don't necessarily need to do that in class, but certainly if there's something that even if the video wasn't super clear, happy to do that. We can also review, and if he has some review materials, we'll go over that, or really any questions you want. But you should definitely, on Tuesday, come to class with questions. And just for my own sake, has he said if solving differential equations is going to be on your exam on Wednesday? He hasn't said anything. Okay. Because certainly if you look at the homework assignments, but it's not due until after your exam. So right? Because your exam is on the 19th and the 7.4 stuff is due on the 21st. So my guess, and certainly the exam I wrote, doesn't have any solving of differential equations on it. So if that changes, let me know. We'll do some practice, more practice. All right, but let's look at these. So there's a couple homework questions that people had. So let's look at, let me do that today. Cool. All right. So this is from, and yeah, some of these are assigned or due, whatever. I don't have any feelings about that. So 7.2, 7.1 was, did I not print out the right pages here? Yeah, I want to start with 7.1. I stapled them weirdly though. Really, what did I do here? Sorry, one moment while I figure out what's on my page here. This is the right page, maybe? Yeah, there we go. Okay, 7.1. All right. 7.1. Sorry, one second. Line here. 7.1, I think there were questions about number 14 and number 16. Look at number 14 first. And these, so I will point out, these questions are really more about your ability to read than about your ability to math. I mean, it's also math, but it's really about like reading stuff and be like, okay, what does that mean? So here's what number 14 says. The Noyes-Whitney equation for the dynamics of the drug concentration is the following. dC dt is equal to K times CS minus C. As an aside here, I would note that T is the independent variable and C is the dependent variable or the function. So not that we're going to, but if you were trying to solve this differential equation, the solution would look something like, would be something like C as a function of T equal to whatever you actually found the function to be equal to. Right? That's the whole idea, right? T is the input, C is the output. So C as a function of T is the thing you would be trying to solve for if we were trying to solve it. But that's what the question's asking. So the question says K and CS are positive constants. So it might be worth noting that K and C sub S are both positive constants. So notably here, even though, and I don't love this notation they've chosen, but what they've chosen, CS is not the function, right? It's just some constant. C is the function. CS is 5, 2, whatever number happens to be. Is this differential equation pure time, autonomous, or non-autonomous? Let's see. So is it pure time? So does your derivative depend solely on the variable t? Absolutely not. Is it autonomous? Does it depend only on, I feel like only is too strong a word here. The only things we're really looking to see depends on is either time or the function itself. So either does it depend on the independent variable or the dependent variable? So does dc dt equal some function of just c? And we would say yes, right? Because the only other things in there are constants and those just kind of get caught. Yeah. So the answer here is definitely yes, it is autonomous. So certainly it is also not non-autonomous. Non-autonomous feels like a real kind of just like, well, we talked about two things, then everything else is over here, right? A non-autonomous feels kind of like a cop out, but okay. Let's see here. So state in words what the differential equation says about how drug dissolution occurs. Sure. So here I'm just going to write words that seem to make sense to me. So dc dt, cool. The rate of change. And let me actually write this. Let me write down the differential equation again. dc dt is equal to k times some constant cs minus c. I wish they told us what cs was supposed to represent, but they didn't. So dc dt is the rate of change of c, where c is supposed to be what? The concentration. So the rate of change of the concentration. Okay. In English, the equal sign translates to what word? And that's the next thing I'm going to say. There's a real important word. The rate of change of the concentration is, that's what equals typically corresponds to, is the K is proportional to, in fact, it should be like this. So here's what dc dt is. It's the rate of change of the concentration. The equal sign is the proportional to is my k there. I'm running out of room for my arrows. And finally, the CS minus C is the difference between the concentration and whatever CS is, probably some limiting value. So proportional to the difference between CS, whatever that is, and our concentration. Or the concentration. It's not ours, it's the concentration. But whatever, all these. Yeah. Yeah. CS is probably like the saturation point or something, the maximum concentration, because I'll point out CS is in equilibrium here, right? So if we had a concentration of CS, it wouldn't be changing. And as C gets closer to CS, this difference is going to be still positive. Okay, let me back up a second. I'm coming at it from the assumption that C is less than CS, right? The concentration is smaller and it's kind of building up. So if C is less than CS, CS minus C is positive. This rate of change is positive. So dC dt, C of t is increasing. As we get closer and closer to CS, this difference gets smaller and smaller. This rate of change gets smaller and smaller, but still positive. So we're getting closer and closer and closer as we go on and on and on. Seems plausible. Not a good test question, right? No, I guess I can see the Dell asking it, to be honest, but most people will be like, that's a terrible test question because I don't want students to write all these words that it's going to be hard to grade. Okay, last part of this question. Verify, I might have enough room here, sure. So verify that I'm going to write C of t, even though they didn't write that. C of t equal to CS times 1 minus e to the negative kt is the solution. With initial condition C of 0 equal to 0. All right, so all we're going to do to verify that something's a solution is look at your differential equation. Say, okay, I need to find the derivative of C, plug that in here, and just plug in whatever C is equal to right there. So the derivative of C, all right, so C prime of t is equal to CS times the derivative of 1 minus e to the negative kt is going to be 0 minus e to the negative kt times negative k. So I'm going to say it's positive k times e to the negative kt. And then we're just going to jam those things into our equation appropriately. So C of t, all that is going to get plugged in right there for C. And C prime of t, all that is going to get plugged in right there to dc dt. Sure. The thing I don't like about plugging in things into both sides of this equation is like you're kind of assuming they're equal to each other when you're supposed to be showing it, kind of. But sure. So I'm going to say that the left-hand side is obviously just going to be the derivative, which is cs with an s times k e to the negative kt. That's kind of obvious. Or not obvious, but it doesn't change. The right-hand side is going to be k times cs minus this whole thing here. I am going to do one thing here. Instead of writing this as is, I'm going to distribute the CS to each of those terms. There's going to be minus CS minus CS e to the negative k. The CS minus CS cancels. A minus is plus. It's going to be plus k times CS e to the negative kt. Are those the same? Yes, they are. We verified it. The left-hand side is equal to the right-hand side. I never used the fact that C of 0 is equal to 0. Oh, well. Maybe we didn't need to. Sometimes they give you more information than you need to try and be tricky. Questions or comments about any of this? This next one is one I remember doing before, which always feels super tricky. Okay, let's look at the next one in this section. Again, this is section 7.1. We're 16 now, which, yeah, I know it's a problem. It's supposed to turn in. I don't actually care that much. Sure. So here's this one. Yeah, this one let's read the problem. So here's the first part. Suppose that the per capita growth rate. Per capita growth rate. Well, let's actually continue. Of a population of size N. Okay, so our population at time t is N of t. The growth rate, aka the rate of change, is just dn dt or n prime of t, whichever way you want to write it. Although I feel like we typically use more the ddt notation versus the prime notation. Okay, but that's not what they said. They didn't say the growth rate. They said the per capita growth rate. Meaning, I don't care that the population is growing at 1,000 people per year. I care that the population is growing at 1,000 people per year per the 60,000 people that live in the town, right? That's the more useful piece of information. By 1,000 people growing per year, that doesn't mean anything really if you don't know how many people there are to start with. If it's in Davis, that's significant. If it's in New York, it is not. So that's why the per capita growth rate is a more important piece of information. So the per capita growth rate is the rate of change, dn dt, divided by the population size, n of t. The rate of change of the population divided by how much population there is. Okay, so they tell us that the per capita growth rate, this thing here, they're telling us that this thing declines linearly from a value of r when n equals 0 to a value of 0 when n equals k. Okay, so here's what we should really read from this. This thing here is a linear function. Or I should say, there's a linear relationship involving this. So we're saying basically, when you plug in n equals 0, that feels, I don't even love, that seems terrible. I don't like that at all. Yeah. How do you do this? See, this is where I always get thrown around here. I'm like, how are we supposed to do this? Let's see. So let's go look and see what else we're supposed to get here. So the problem then says, show that the differential equation for n is so we want to show, we want to show that we're supposed to get dn dt is equal to r times 1 minus 1. That's a 1, believe it or not, minus n over k times n. Yeah. Good question. How do we do this? Let's see here. Per capita growth rate declines linearly from a value of r 0. N equals 0 thing is what's throwing me off here for a second. So let's just think about how we graph this. So typically, if I was graphing the phase plane, I'd have n over here and dn dt over here. Yeah, per capita growth rate. Let me see. Let me read this again just to make sure I'm not missing something stupid. Hmm. Yeah. So here's what I wanted. Here's what I wanted to do really. I want to say dn dt divided by n should equal r over 1 minus n over k. Let's take a look at that for a second. So kind of ignoring the fact that you're going to get division by 0 over here if n is 0. That's just, we have to ignore that. So let's ask ourselves a question. First of all, although it's kind of hard to see, is this a linear function of n on the right-hand side here? Totally, right? It's just some multiple of n plus some constant. If I plug in n equal to 0, do I get this is equal to r? I sure do, right? If n equals 0, then we certainly get dn dt divided by n equal to r times 1 minus 0, which is r. If n equals k, do I get that my per capita growth rate is equal to 0? I certainly do. I get r times 1 minus k over k, which is 0.
Why don't we plug it into the amount?
Because that would be problematic. Because honestly, because I'm kind of avoiding that, to be perfectly honest. I'm trying to make it make sense in my head. I'm like, why don't we do that? And I don't have a good answer. So I'm kind of just ignoring it, to be really frank. Yeah, because the problem I'm having here, no, am I having this problem? No, I don't think I am. Yeah, I'm totally okay with everything we've done here. Yeah. Yeah, per capita growth rate's a little funky. It's because you can kind of say like, so what we're really saying here is that the population is 0 people. Kind of doesn't make a whole lot of sense, but we're going to say it anyway. But the population is growing at a rate of R. Well, I should say that the relative growth rate, right? The per capita growth rate. I don't love it. But we can make it work. We can make it work to answer the question you're asking, which is that, yeah, certainly if we say that the per capita growth rate is equal to this linear thing, then we can just move this n over here to get back to there, which is what we were trying to show was actually the differential equation. So kind of weird. Yeah, it's kind of weird. And it kind of looks like this, where this point here is the point k comma 0, and this point here is the point 0 comma. It certainly makes more sense if we write it like this, right? Because then you're not having division by 0. But yeah, I don't love it. It's not about, I have to go think about it some more and think about it. Like, there's probably some nuance here that we're maybe missing just a little bit, but as far as answering this question goes, that's kind of all there is to it. All right. Let's look at the other questions from section 7.2 that were asked about. And I don't remember which ones they were. Yeah, 6 and 14 and 18. We might not get to do all these, but we'll do some of them. So 6, I feel like, isn't too terrible. So question 6 just says the following things. Find all equilibria of the autonomous differential equations and construct the phase plot. So let's look at the one that looks, we'll look at the two that look the most egregious. We'll look at 6a and 6c. So the first one, 6a, is y prime equal to y squared minus a over y plus 1. And we're given that a is between 0 and 1, and y is bigger than -1. You don't really have to think so much about this other than just making sure it doesn't impede any of the solutions you find. So the only reason we're really saying y is bigger than -1 here is so we're not dividing by 0. And then a is between 0 and 1. We need a to be non-negative to get like solutions. I'm not exactly sure why a has to be less than 1, but okay, fine. So how do you find equilibrium? Right, set the whole thing equal to 0. Don't worry, it says all equal to 0. The denominator is kind of out of play already. So really that's just going to be setting the numerator equal to 0, which means we're going to get y squared equal to a, which is non-negative. Cool. That needs to be true to solve this. And then y is going to equal plus or minus, plus or minus the square root of a. And I'll point out that both of these are solutions because since a is less than 1, the square root of a is less than 1, or it's if the negative square root of a is bigger than -1. So the square root of a is certainly less than 1, the negative square root of a is bigger than -1. So it's still within the bounds of where y has to live, so it does count as a solution we have to consider. That's probably why they said a had to be less than 1. And then we want to draw or construct the phase plot. All right, cool. Yeah, maybe cool. So I've got y on the horizontal, y prime on the vertical. So when they say construct the phase plot, what they really are saying is to draw this graph, right? We're just trying to graph g of y equal to y squared minus a over y plus 1. So I know that if y were equal to -1, I have a vertical asymptote. Let's draw it way over here. And then we know that we're going to have equilibria, aka horizontal intercepts or x-intercepts at negative root a, let's put it like right about here, and positive root a. And then our job is to figure out if we're positive or negative over here. I will point out the denominator is always positive, right? Whatever y is, if y is bigger than -1, y plus 1 is always going to be positive. Y squared minus a is going to be positive if y is bigger than root a or more negative than negative root a. So it's going to be positive. In fact, it's probably easier to look at the in between. If y was 0, your numerator would definitely be negative and your denominator would definitely positive. So if y is 0, we get like negative a. And then left of negative root a, we're going to be positive. I'm not really sure what happens over here. Probably just something like this, though. There's my phase plot. They don't ask us to classify any equilibria here, which seems like a real missed opportunity.
Wait, can you explain how you just do that one time?
Sure. So I'm looking at each of these three sections between -1 and negative root a, between negative root a and positive root a, and to the right of root a. And what I'm really doing is thinking in my head, if I plug in something in each of the sections, is my y prime, the thing I'm trying to graph, is it positive or negative? So I started in between negative root a and root a because 0 is an easy choice. So I'll point out, so when y is between negative root a and root a, we're going to pick y equal to 0. And then my g of 0, just plugging that into the name I've given the function, right, g of y, is going to be 0 minus a over 0 plus 1, which is negative a, which is certainly negative. So I know that between negative root a and root a, the function is negative. And then a couple ways to argue the other 2 points. So I didn't even say really much about the other one because I know that each of these 2 roots have a degree of 1 or a multiplicity of 1, meaning we have to cross. Because really they came from factoring y squared minus a as y minus root a times y plus root a. But another way to go here is to pick, say I pick something bigger than the square root of a. And I squared it, I'd have a number that was bigger than a. And then subtract a, well, that's still positive, and the denominator is always positive, and positive divided by positive is positive, so it's positive over here. Same argument can be made over here. I pick a number that's less than negative root a or more negative than negative root a and square it, that number is going to be bigger than a. Subtract a, still positive, divide by this, still positive because that number there isn't as negative as -1, so whatever I'm plugging in for y, it's not as negative as -1. If I add 1, it's still positive. So that's how I'm getting that this region is positive and this region is positive. But really the fact that I was using was that y squared minus a is equal to y minus root a times y plus root a. And I know that if it's negative here, since both of these factors have odd multiplicities, I have to change from negative to positive and from negative to positive at these 2 points. Or cross if you prefer that language. Okay, let's look at 6C. I think 6B is very doable. I don't think we can talk about that one. Let's look at 6C, which looks equal. Equally is maybe not the right word, but certainly looks also funky. So this one says you have y prime equal to a over b plus y. minus 1. And we're given some conditions. A is larger than B is larger than Y, which is bigger than, oh, sorry, is bigger than, nope, I made a mistake there, sorry. A is larger than B is larger than 0, and Y is bigger than or equal to 0. Okay. Find the equilibrium. So we're going to just set this whole thing equal to 0. Set A over B plus Y minus 1 equal to 0. I don't need to get a common denominator here, although it might be helpful in the future, but I don't care right now. I'm going to add 1. A over B plus Y equals 1. Multiply by B plus Y. So A equals B plus Y. And then A minus B is equal to Y. That's my equilibrium. Notably, it is a valid one because since A is bigger than B, A minus B is positive and Y can't be negative. So we're good to go there. All right. Then we have to draw the phase. Okay. So I'm trying to graph G of Y equal to A over B plus Y minus 1. It might be helpful here to get a common denominator over here to make it easier. So I don't know if this is actually going to help, but I'm going to do it. I'm going to write it as A over B plus Y minus B plus Y over B plus Y, which then becomes A minus B minus Y over B plus Y. Is that going to help me graph it? Maybe. Okay, so just graphing a rational function like I normally would, I see that this rational function is going to have a vertical asymptote at negative b. And then it's going to have a horizontal asymptote, which may or may not be important, at negative 1. I don't know if I really care about that horizontal asymptote, but I'm going to draw it anyway. I know I have, well, let's actually find my y-intercept as well. Might as well. So if I plug in 0 for y, I get A minus B divided by B, or A over B minus 1. Since A is larger than B, and then sure, so G of 0 is going to be A minus B over B. And since A is bigger than B, this is positive. So I know I'm living somewhere like here. And then I know that my horizontal intercept, aka my equilibrium, is A minus B, which is also positive. A minus B comma 0. This is 0 comma A minus B over B. Okay, I think I can graph this now because that's my only horizontal intercept. So I kind of have to do this. If it were me and I were a student, I was kind of like, well, I might use some Desmos. So I'll just point out, you could totally do this with Desmos. Let me show you what I mean. And I do think it's worth your while to play with Desmos, as I've said many a time. So let's say I wanted to graph something like, and I'm going to use X instead of Y for graphing it. So I'm going to do, actually, no, I'm going to use Y. Maybe, we'll see. Let's see. G of Y, we'll see if this works, equals A divided by, let me go back here. I do want to add a slider for A. Divided by B plus Y. Yes, I want to add a slider for B as well. Minus 1. And then we can say, well, we know that A has to be bigger than B and they're both positive. So let's say that like A is 2. Well, let's go 3 even. A is 3 and B is 1 point, or let's say B is 2. Yeah, that graph looks reasonably like the thing, or at least the right-hand side of it, because I didn't draw the left-hand side of it. But that looks totally plausible, right? My vertical asymptote's over here. My y-intercept, or my vertical axis intercept, is positive, and my horizontal axis intercept is also positive. So we were able to figure that out based on this. Kind of weird though. I would this would be, in my opinion, a much better or more approachable question if they gave you real numbers for A and B, as opposed to just saying A and B. But still manageable, we should be a little more thoughtful. Okay, let's. What else is on this list here? 14. Yes. So the way I found the exit, well, let me ask you, what do I usually do to find the x-intercept? Or also known as the equilibrium here. The whole thing equal to 0. So I set the whole thing equal to 0. I decided to add 1 over there, multiply both sides by the denominator, and then solve for y. Cool. Okay, we'll look at 14. I don't think we're going to get to 18 because I do want to talk about some of these differential equations or solving differential equations. Yeah. So these problems are just kind of long and gnarly. Here's 14. So let's see what we do. Suppose the population grows according to the logistic equation, but is subject to a constant total harvest rate H. If N of T is the population size at time T, the population dynamics are as follows. The rate of change of your population, N, is equal to R times 1 minus N over K. By the way, you see this a lot. You're going to see a lot of R times 1 minus N over K. Times N, no, sorry, I'm looking at the wrong thing. No, still this times N, cool. And then minus H. So this is that same kind of thing we set up in that other problem that was kind of funky, where we were talking about how the relative growth rate, or there's another word for it, the relative, whatever, the relative growth rate, whatever else you want to call it, was linearly declining from N to K or whatever, and now we're just subtracting off this harvesting. Different values of H result in different equilibrium population sizes. If H is large enough, we might expect extinction, right? If you're harvesting too much of the population, it might not make it. Suppose R equals 2, K equals 1,000, and H equals 100. Find all equilibria. Okay, so we're just going to throw in our numbers and set it equal to 0. So dn dt is equal to 2 times 1 minus n over 1,000 times n minus 100. And unlike some of the previous problems we've done, finding the equilibrium here is a little more work because it's not just factored for us already. So we have to kind of like actually multiply it out and then solve. So if set this equal to 0, so I'm gonna point out that this is like a 2n multiplied by this insights here. So 2n times 1 is 2n. 2n times n over 1,000 is 2n squared over 1,000 minus 100 equal to 0. And I'm going to make my life easier by multiplying the whole thing by 1,000. Or I guess I should say really 500, right? Because this is, right, 2 over 1,000 is 500. So I'm going to have 500 times 2n minus 500 times 2n squared over 1,000 minus 500 times 100 equal to 0 times 500. And then simplifying this, this is going to be a negative n squared. I should have made it negative 500. Oh, well. 500 times 2n is 1,000n. And 500 times 1,000 times 100 is 50,000. Minus 50,000. And then I would have changed the signs. N squared minus 1,000n plus 50,000 is equal to 0. And I'd really love to say that that factored. I have no idea if it factors. I personally cannot, off the top of my head, think of numbers that multiply 50,000 and add up to 1,000. But I wish I could. I don't really want to use the quadratic formula here. Boo. Fine. So we're going to get n equal to negative b plus or minus the square root of b squared, which is going to be 1,000,000 minus 4 times 1 times 50,000 No, it's not going to factor nicely. That's terrible. Over 2 times a. So this ends up being 1,000 plus or minus the square root of 1,000,000 minus 200,000 is 800,000. And that is not a nice square number. How unfortunate. So there's our two equilibria. I will point out that both of these equilibria are positive because the square root of 800,000 is less than the square root of 1,000,000, which is 1,000. So you have 1,000 minus a number less than 1,000 divided by 2, and 1,000 plus a number less than 1,000 divided by 2. Okay, I guess we should do the second part, which is determining if they're stable or not. Okay, so base plane time. I feel like I can fit it in up here because it's not that dire. So I would point out that we know that this, so looking at this differential equation here, before I multiply both sides by 1,000, what kind of graph is that going to have? Right. Or let me ask you a different question. What's a good name for this equation that is 2n minus 2n squared over 1,000 minus 100? It's not linear, it's a quadratic or a parabola. Which way does it open? Downwards, because it's a negative 2 over 1,000 times n squared. Right? Before I manipulated it, it was definitely opening downwards. So we know it's going to be opening downwards, something like that. And my two equilibria are annoyingly the 1,000 plus the square root of 800,000 all over 2, and the 1,000 minus the square root of 800,000 all over 2. Which one is the stable one? The bigger one or the smaller one? I see you whispering it on your lips. Yes, it is the bigger one. This is the stable one because, right, we're increasing on the left of it and decreasing on the right of it. Whereas this other one here is the unstable one, right? Specifically, if you're bigger than it, you're going to be okay. You're going to survive. But if you're smaller than that unstable equilibrium, you're going to die out, right? That's your harvesting rate is too great for that little people or that little whatever things we're talking about, and you're going to eventually not make it. All right, cool. All right, let's spend some time talking about solving differential equations, which I know we talked a little bit about last time. We'll try and get at least one example of what he's going to do on Friday because I do think it's worth seeing before you see it. But let's solve some differential equations. And I will remind you all that at this juncture, the only method you have available to you is separation of variables. So not on this exam, hopefully, but on the next exam, when you're asked to solve a differential equation, you're going to ask yourself, can I separate the variables? If the answer is no, then you're going to try the other thing we haven't talked about yet. But for now, that's all we've got. So let's look at this equation. Let's look at, say, for example, I feel like we might have done this one already, but oh well. I don't think we did, but I can't remember for sure because there's so much math in my life. So here's our first differential equation. X squared plus 1 times y prime equals x times y. So the first step is to to separate the variable. I mean, so I would say the first step, which we are going to skip here because it's already done for us, is to make sure that you either have y prime by itself or y prime times some stuff. Meaning if you have things added or subtracted to y prime, you should bring them over to the other side. So if we had started with x squared plus 1 times y prime minus x times y equal to 0, then the first step would have been to add xy to both sides so that you could have y prime times some garbage all by itself. But then, once you get to this stage here where you have y prime times some stuff all by itself, the only things we're allowed to do are multiplication and division. Anything else will screw things up for us. But we should also make one change. We should rewrite it as x squared plus 1 in parentheses times dy dx equal to x times y. And I would say specifically when you're separating variables, you kind of have to use this Leibniz notation. You are stuck using the dy dx or the dn dt or the whatever the d on the top and the d on the bottom are. Because you have to write it as dy dx so you can separate the y's from the x's. whichever side dy is on, that's the side the y's need to go on. And since dx is on the bottom here, it needs to go over to the other side. So let's see, moving my y's to the left and my x's to the right, I'm going to have dy divided by y. And I'm going to have x divided by x squared plus 1 times dx. Whenever you're doing this, your dy and your dx always have to end up in the top or not in the denominator. And then we're going to integrate both sides. You can write this as the integral of dy over y, or if it's more comfortable, the integral of 1 over y dy equal to the integral of x over x squared plus 1 dx. Since not all of you were here on Tuesday, I am going to say this again, although I promised I would try not to say it every time, but I'm going to say it this time. He did also mention this in class yesterday, but I think it's worth repeating. When we integrate 1 over y, do I have initial condition? No, I don't. Okay, fine. So when we integrate 1 over y, it's going to be the natural log of the absolute value of y. And after this, I will try my best to say we can usually just ignore that absolute value. And you'll see why as we do this example. On the other side, I feel like this is something you should all be able to integrate really quickly. Like it's going to be the natural log of the absolute value of x squared plus 1, almost. But if I took the derivative of that, I would get 1 over x squared plus 1 times what? But I don't have a 2x, I have a 1x, so I need to multiply by 1/2 or divide by 2 to make sure that works out. So we technically did a little u substitution there, but I will say if you can see that the numerator is essentially the derivative of the denominator, you're going to get the natural log of your denominator. In fact, that's kind of a rule people talk about sometimes, right? Is that the integral of g prime of x divided by g of x is equal to the natural log of the absolute value of g of x. And then you can always adjust for a constant multiple. Cool. And then a plus c. Now, someone asked last time, I think it's worth repeating again here, that I would just put the plus c on the right-hand side. They're like, why? Well, because if I put plus c on both sides, let's say I put a plus c1 over here and a plus c2 over here, I can just subtract c1 from both sides and say that c2 minus c1 is my new constant c. So here's my rewriting. Natural log of the absolute value of y equals 1/2 the natural log of, check this out, parentheses x squared plus 1 plus my constant c. Why parentheses? Because x squared plus 1 is already always positive. So we don't need the absolute values. They are a moot point. Okay, now we're going to solve for y. You can't always solve for y. Most of the time, the problems you're faced with, we can, but occasionally you're going to be stuck with something where it's like sine of y plus the natural log of y equal to x cubed, and you're not going to be able to isolate y. But most of the time you can. So here we're going to have e to the natural log of the absolute value of y equal to e to the all this stuff, e to the 1/2 natural log of x squared plus 1 plus c. Okay, there's always two things we do with this e to the something plus c. We're going to break it apart as e to the something times e to the c. And I'm going to do two things at once here. With the left-hand side is going to be the absolute value of y. The right-hand side is going to be e to the 1/2 natural log of x squared plus 1 times e to the c. And usually we would skip this next thing I'm about to say. And in fact, he did skip it in class, but I'm going to say it. So normally you're just going to jump to saying e to the c is a new constant a. But what's happening with the absolute values there is saying, oh, yeah, if the absolute value of y is equal to all this stuff, that means y is either equal to plus or minus all that stuff. I'm going to write the e to the c first. I'm also going to make another simplification over here. I'm going to write this as e to the, check this out, natural log of x squared plus 1 to the 1/2 power. Bringing that 1/2 up as the power of x squared. God, that looks really great. I'm not a fan. I don't think there's anything in D right though. That's not really that slightly better, I guess. Okay, so here's the deal. The plus or minus e to a constant is a constant. We don't know yet if it's positive or negative, but it's going to be one of them. And so we're just going to say it's some constant. I usually like to use the letter A. I think Del does as well. Great. So we're going to say y equals A times e to the natural log of some stuff is just the stuff. So there's our final solution to the differential equation if we don't have any initial conditions to plug in, which we don't. So if they told us that, like y of 0 is equal to 7, then we would have plugged in 0 for x and 7 for y and solved for the constant a. But without that, this is our general solution. And this is your typical process. You separate your variables, you integrate both sides, and then you solve for y. Solving for y can be really kind of a grab bag of different things, right? Because maybe you're going to have natural log of y, maybe you're going to have something else. So it really kind of depends on what we have. Let's look at some more examples. I really feel like I'm looking at the examples I did last time. But yeah, I for sure am. Okay, move. Let's not do that. Pardon me one moment, please, while I look for more examples. Those are the same examples. Wow, did they really not bring in other examples? That's really not great. No, it won't be that. Sorry, I feel like I'm underprepared here. Fine, let's make some shit up. Um, let's say we want to solve the following differential equation. Let's say we have the following. Y squared times dy dx is equal to 1 over x squared plus 1. And I feel like it's kind of a cop-out because it's almost already separated for you. Let's go ahead and separate these variables and see. Oh, and we'll do that. And we know that y of pi over 4 is equal to, say, 8. Pi over 4. That should feel like a hint, maybe. No, pi over 4 is the wrong number. Apologies. Sorry. That's what happens when you make things up. Y of 1 is equal to 8. That's less of a hint, but might already give away the game. So we're going to separate. It's not that exciting here because it's kind of already separated for us. In fact, why don't you all separate that and do some integration? While I look around my notes here and see if I have anything else exciting. Oh, there it is. There's a few things. Cool. Oh, we should do a tank problem. Yeah. So there's our one-step separation. This is brought dx over to the other side. Now we're going to integrate both sides. If the integral y squared dy equal to the integral 1 over x squared plus 1 dx. The left-hand side should be pretty straightforward. It's going to be y cubed over 3. The right-hand side, or what the integral of 1 over x squared plus 1 is? Yep, exactly. It's going to be the arc tangent or the inverse tangent of x plus c. And now we're going to solve for y. Now, yeah. Oh, I definitely, that's kind of backwards from what it meant to be. So, deciding when you want to solve for your constant is kind of an art form. So if we plot, or actually not yet, I'm going to multiply both sides by 3. Let me say that y cubed is equal to 3 times the arc tangent of x plus 3 times a constant is still a constant. And usually we don't even change the name of it. We just say, great, it's still a constant. If you prefer, you can be like, yeah, this one is C1, this one is C2, if that makes you feel better. But no one is doing that. And then now might be the best time to actually find C. Because the only other thing I have to do here is cube root both sides. But I'll point out that if I cube root both sides and get y equal to the cube root of 3 arc tangent of x plus 8, sorry, plus C2, sorry. Not 8, it's definitely not 8. If I'm going to solve for C2, I'm going to have to end up cubing both sides to get C2 by itself. So this would have been the right spot to actually plug in x equal to 1 and y equal to 8. I think I might have gotten slightly backwards, but it's fine. So plugging those in, we have 8 cubed equal to 3 times the arc tangent of 1 plus our constant c. I would just leave 8 cubed as 8 cubed, although it is equal to 512. So we have 512 minus, what's the arctangent of 1? Right, that's what I was thinking before. So it's 3 times 5 over 4 equal to C2. So that number, it's kind of gross, that's what's going to get plugged in for C2 there. So our solution here is going to be y equal to the cube root of 3 arctangent of x plus 512 minus 3 pi over 4. Sometimes the constant you find is just kind of weird. How much time do we have? Okay, we got time for at least one more simple before we do one other thing. Let's take a look at, let's look at that one. So we have the following. Yeah. So I have to make sure that looks okay. Sure, let's look at this one. Y prime is equal to x over y minus x over 2 plus y. Okay, so let me ask you all a question. Is y prime already all by itself? Cool. So what are the only things I'm allowed to do at this point? So one time? Yeah, but what operations are the only operations I'm allowed to use? Right, multiplication and division. Let's rewrite it as dy dx. So dy dx equals, I guess I want like a common denominator. Oh wait, what can I factor out from both sides here? X. I'm left with a 1 over y minus a 1 over 2 plus y. Which seems like it's going to be kind of terrible. Okay. So we're going to bring our x's to the left, our x's to the right, our y's to the left. So we're going to have dy divided by 1 over y minus 1 over 2 plus y equal to x dx. It is probably well within our needs here to simplify this, right? Integrating that's going to be totally awful. So let's see. If I just simplify 1 over y minus 1 over 2 plus y by getting a common denominator, multiplying this by 2 plus y over 2 plus y, and this by y over y, we end up getting 2 plus y minus y all over 2 plus y times y, which is just 2 over 2 plus y times y. And then if you take the reciprocal of that, it's going to be actually lovely, right? Because we have, so here's what we have. We have dy divided by that, which is 2y over 2 plus y times y equal to x dx. But then we take the reciprocal of that, it's actually great. So the reciprocal here is going to be 2 plus y times y all divided by 2 dy equal to x dx. And now we're going to integrate both sides. This left-hand side, I probably still made not as nice as possible. I can certainly factor out the 1/2. I have 1/2 times the integral of 2 plus y times y. I'm just going to distribute the y and get 2y plus y squared. On the right-hand side, I might as well integrate x and get x squared over 2 plus c. And then on the left-hand side, I'm going to have to integrate this. So I'm going to get 1/2 times 2y squared over 2, which is just y squared, plus y cubed over 3 equal to x squared over 2 plus c. And really, I can't solve for y here. Interesting question. But I can, I guess, multiply both sides by 2. So kind of my final answer is y squared plus y cubed over 3 is equal to x squared plus a constant. I multiplied x squared over 2 by 2 and got x squared, and the constant times 2 is constant. Yeah.
So you don't multiply that constant, or you don't show it because it'll, the way it'll all play out, it'll just be like as if you multiply it.
Right, because if I multiply both sides by 2, 2 times x squared over 2 is x squared, but 2 times a constant is still a constant. Yeah, so whenever you add to a constant, subtract from a constant, multiply a constant by a constant, or divide a constant by a constant, it's still a constant. And so we just say it's kind of the same thing it was, even though technically it's changed. All right. Yeah, that one's a little unsatisfying, but it's fine. Let's go ahead and look at a question that is a little bit more interesting. And yeah, sure. So in class, I think at the end of class, he talked about a tank problem, or he talked about sugar or salt and like a thing. That's a pretty typical setup, and it leads to a differential equation, especially the one he did, leads to a differential equation that isn't solvable as a separable differential equation. So let's actually, let's start. I don't think we need to go through the whole setup, although we'll talk more about that later. Let's try and solve. Yeah, let's look at that one. Sure. Yeah. So here is a differential equation that we would like. Oh, actually, no, I got all these. I do have. Sorry, 1 second. There we go. Yeah. Let's say we want to try and solve the following differential equation. Y prime equal to, let's say x minus 3y. I want to point out this is not separable. So if your differential equation is not separable and we're asked to solve it, then it has to be a first order linear differential equation. It is a first order, meaning only the first derivative and no other higher derivatives. Linear, meaning you only have y to the first and no other powers of y, differential equation. First order just means y prime only. Linear means y to the first only and no other powers. And unfortunately, those look kind of similar to each other. To make sure your prime looks like it's an angle and your 1 is not. Okay. So if we have a first order linear differential equation, we have to write the differential equation in the standard form, which is not currently written in. So the standard form of a first order linear differential equation is the following. It's your derivative y prime plus whatever your function of x is multiplied by y to the first. We usually call it p of x or p of t, depending on what your variable is, equal to whatever is left over in terms of x. Notably, it's first order, right? You have a y prime, and it's linear. You have a y to the first, and that's all we care about. So after you write it in this format, we have to find a few things. We're going to find what's called the integrating factor. Usually labeled as mu of x or mu of t. And it's equal to e to the integral of p of x dx. And typically Dedel is a fan of kind of seeing all this work, I think. So we'll kind of go through the whole process of why this works. So so in this case, right, for our problem, our p of x is equal to, actually, let's write it out. So we have y prime plus 3 times y equal to x. So our p of x is just the function 3, which is not that exciting. And our q of x is just equal to x. Our integrating factor, mu of x, is going to equal e to the integral of 3 dx. The integral of 3 is just 3x, and we do not worry about a plus c here, or any absolute values or any, like, it's very, very basic. Okay, So here's what we do with this. This integrating factor, we're going to multiply the entire equation by that integrating factor. So we're going to multiply the whole equation by whatever mu of x is equal to. In this case, e to the 3x. Okay, check this out. On the left-hand side, we're going to have, we're going to have e to the 3x times y prime plus e to the 3x times 3 times y equal to x times e to the 3x. And here is what is true every time we do this. The left-hand side looks like it's the derivative of a product. Specifically, this left-hand side here is the derivative of the product of e to the 3x and just y. So let's think about a product rule. So product rule is the derivative of one thing times the not derivative of the other thing. So y prime times e to the 3x plus the derivative of the other thing. The derivative of e to the 3x is e to the 3x times 3 times the not derivative of the other thing, which is y. It always works. And I can show you more about this in a minute if you want. So here's what we're saying then. I mean, you need more paper here. So come on, paper. So what we're saying here is that, hey, look, the derivative of e to the 3x times y is equal to x e to the 3x. Cool. If I know the derivative of something is equal to something else, if I know the derivative of e to the 3x times y is equal to that, that means I can say that e to the 3x times y must be equal to the antiderivative of x e to the 3x. And then, without integrating yet, even though we could integrate, if I just solve for y, my solution, which we're not really done with yet, but I'm going to write this anyway, is y equal to 1 over e to the 3x times the integral of x e to the 3x. Two things. Thing one, don't make the mistake I made when I was a student and think that you can cancel those e to the 3x's. They do not cancel yet. You have to do the integration here before you think about any sort of cancellation. Thing two, this is the general way of writing the solution. So a lot of times people are like, some teachers, probably not to know, is like, you can skip straight from finding this integrating factor and getting to the solution, which is the solution is equal to y equals 1 divided by your integrating factor times the integral of whatever your q of x times your integrating factor is going to end up being. So oftentimes you can just skip this whole process of be like, oh yeah, multiply everything by the integrating factor, see the left-hand side is the derivative of a product, anti-differentiate both sides, and then solve for y. But I feel like Dell in the past at least wants me to show this work. So he'll certainly talk about it on Friday. He might say about whether or not you need to show that. So the rest of this is just solving for this integral here. So if I integrate this, I have to use integration by parts. So integration by parts, we're going to let u equal x. dv is the rest, e to the 3x dx. du is 1 times dx. And v is 1/3 e to the 3x. So then we're going to end up getting that y is equal to 1 over e to the 3x. A lot of times I'll rewrite this as e to the negative 3x times, let's see, it's going to be my u times my v. So x times 1/3 e to the 3x minus the integral of v du, which is 1/3 e to the 3x dx. So that's going to be giving us that y is equal to 1 over e to the 3x times, I'm going to simplify this a little bit and write it as like 1/3 times x e to the 3x minus The integral of 1/3 e to the 3x is 1/3 e to the 3x divided by another 3, so it's going to be 1/9 e to the 3x. And here is the super duper important part. Plus c in those brackets that gets multiplied by the 1 over the thing out here. So it is vital when you do first order linear differential equations that when you do this integral gets multiplied by 1 divided by your integrating factor, and the plus c is included in that. People often like to leave it like this. I prefer to simplify it. So if we simplify it, we're going to get that y is equal to, well, let's check this out. 1 over e to the 3x times e to the 3x cancels out, and you're left with a 1/3 x there. 1 over e to the 3x times e to the 3x cancels out, and you're left with a minus 1/9 there. And if you just wrote plus c, it would seem like a really boring answer. In fact, not only boring, it'd be kind of a wrong answer. So it's really super important that you have plus c divided by e to the 3x there. Otherwise, your answer is not nearly as all-encompassing as it needs to be, right? Without that, it's really, really, really not right. So it's very, very important that when you do this, this 1 over your mu of x gets multiplied by everything, including the plus c. And then if there's an initial condition, we can plug that in to find the value of the constants.
Would that change the speed? Would that just
So it will never be a constant. And here's why. The 1 over e to the 3x is always going to be 1 over e to the integral of p of x. So even if p of x is a constant, like it was in this example, the integral of a constant is going to give you a constant times x. And then e to the something times x will never be a constant. So yeah, you'll never get a constant down there. But good question. That's worth thinking about for sure. Just as an interesting fact, although it's probably not super vital that you know this, but I still think it's worth mentioning, is that the reason this works is because what you're really doing here is you're saying, cool, I have on the left-hand side, yeah, I feel like this is very in the way there. On the left-hand side of this equation, what I really have is e to the integral of p of x times y. And we take the derivative of that, sorry. We take the derivative of that product, we'll check it out. I'm going to do y prime first. I get y prime times the other thing left alone, which is e to the integral of p of x dx, plus, switch it up. We're going to leave the y alone. And then the derivative of e to the stuff is e to the stuff times the derivative of that stuff. What's the derivative of the integral of a function? The function. But I'll remind you all that e to the integral of p of x, that is just your mu of x. Oh my gosh, why do I... No, almost. I'm mad at that pen for being not working. Sorry. So look, I've exactly got y prime times mu of x plus y times p of x times mu of x. It's exactly like the left-hand side of my equation, y prime plus p of x times y, before I multiplied the whole thing by mu of x. So that's why multiplying by mu of x works. It will always, always look exactly like this. Sorry, exactly like this, which will then always be the derivative of the product of the two things. And I'll just point out that is really the product of, right? That's just mu of x times y. So that's why this process works. If you multiply the whole thing by mu of x, the left-hand side always ends up being a product full derivative, and then you can always simplify it this way. It's kind of neat. So a lot of these types of differential equations come about from tank problems. Let me give you, we'll set one up just to kind of talk about something, because there is one nuanced piece here that I think you all want to be aware of. Do I have one right here? Maybe not. There we go. So let's look at this tank problem, which we will try to just say the words about in these last moments here. So tank problem. So here's the setup. I'm not going to write all the words. I'm going to say the words. So a large tank initially contains 100 gallons of pure water. So tank contains 100 gallons of pure water. At time equals 0, a salt solution with a concentration of 2 pounds per gallon flows into the tank at a rate of 5 gallons per minute. So we're putting in a solution. The concentration is 2 pounds per gallon. And the rate that we're putting it in at is, what was it, 5 gallons per minute? Yeah, 5 gallons per minute. And as we were putting that in, we were also draining the well-stirred tank. So we're draining. So we're putting in, draining out. We're draining. And the reason we say it's well-stirred is to make sure that essentially it's was it heterogeneous, homogeneous? I don't know. Whatever the word is for mixed appropriately. So like whatever volume you take out has the same concentration of salt wherever it is. So we're draining it at a rate of 4 gallons per minute. Most of the time for these problems, the rate in and the rate out are the same, which usually makes it a little easier. If they're different, it's a little bit harder. So let's set up the differential equation for this system, and then next week, well, maybe next Thursday, not next Tuesday, we'll talk about how to solve it. So we're going to set up a differential equation for, and this is important, the amount of salt in the tank. Not the concentration of salt, the amount of salt. So we're going to say that S of T equals the amount of salt at time T. And I'll point out that they told us that there was no salt in the tank because it's all pure water. So we know the initial condition is that S of 0 is equal to 0. Here's how we're going to set up the differential equation. So ds dt, that's the rate of change of the amount of salt, is going to be equal to the amount going in minus the amount going out. How much salt's going in? Well, I'm putting in salt in a solution that's 2 pounds per gallon at a rate of 5 gallons per minute. And you can see that the gallons are going to cancel here. We'll be left with 10 pounds per minute. A lot of salt. 10 pounds of salt every minute goes into the tank. How much salt is coming out of the tank? That's a harder question to answer. But the idea persists that it's going to be the concentration of the salt multiplied by the rate that it's going in or out. So the concentration in was easy. The concentration in is just, they told us it was 2 pounds per gallon. The concentration out is changing. So in the beginning, the concentration out is literally 0. But as soon as you start putting salt in and it's well stirred, the concentration is increased. The amount of salt has increased. So the concentration going out is going to be, well, there's an easy way to think about this. It's the amount of salt divided by the volume of the tank. Which if the volume wasn't changing would be easier, but the volume is changing. So the amount of, how much salt is in the tank? S of T. That's part that always took me a while to wrap my head around when I was a student. What's the volume of the tank? Well, it starts off at 100 gallons. And in this case, are we increasing or decreasing the volume every minute? Increasing, right? We're putting in 5 gallons and taking out 4 gallons. So every minute, the tank is going to increase by 1 gallon. So our volume is going to be 100 plus 1 times T. That's our concentration going out. And then the rate it's going out is, again, easy. It's just going to be 4 gallons per minute. And that's pounds per gallon. I like writing the units at first to help me see what's going on. But then if I actually was going to write this differential equation so I can solve it, I would get rid of the units and say, okay, 2 times 5 is 10 minus 4 times S over 100 plus T. And then if we were actually going to try and solve this, we would rewrite it in the standard way of writing a first order linear differential equation. We would write it as ds dt or s prime plus 4 over 100 plus t times s equal to 10. And your 10 would be your q of t, and your 4 over 100 plus t would be your p of t. And then we would use the same process we did before. We'd find e to the integral of p of t. We multiply everything by that. The left-hand side would be a product rule. We integrate both sides and then divide by whatever. Yeah, that's the idea. All right, I should stop at 11:52.